Hello, everyone. I think we're just about to get started here. Looks like everybody has answered the top hat question. So we're talking about the function f of x equals x. Very simple looking function. And let's see if you guys can figure out how to write this. Just get organized here for a second. Okay, here we go. I'm going to reveal the answers. Top hat closed. Let's see, what do people say? So a little bit of a split here. 22% of people think the coefficients in front of sine are 0. 37% of people think the coefficients in front of cosine are 0. And 42% of people think it depends. So we did this last time. Mic's not working. Is it working now? Okay, so we're not working for some people. Okay, good. I'm glad some people are in the chat. That's great. Okay, so this is a little bit of a split. So what I would like is I'm going to open it up again for revoting. And if you chose it depends, then you need to write in chat, what it depends on. So no escaping this time. You have to write in the chat what it depends on if you choose option C. Okay, so I'm going to reopen this again. So top hat is reopen. You can change your vote. So we're talking about the function f of x equals x on 0, 2. So what does that look like? Here's the x-axis, 0 to 2. And we're talking about this function in red. Okay, so I'm back. People in the chat are correctly figuring out that the secret to this problem is to extend the domain. So this interval 0 to 2 does not match it with our minus L to L, which is what the world's most important orthogonal basis, the WMIOB, world's most important orthogonal basis. That's from minus L to L. This is from 0 to 2, so they don't match. So what we need to do is we need to take this function f of x equals x, and we need to extend it to make a function from minus 2 to 2. And it depends, the answer to the question depends on how you do that. So of course you could do that all sorts of ways. You could pick any function you want to go here. So you could do anything sort of crazy. But the nicest thing to do is either make the function even or odd. So what we're going to do is fill in here. We're going to either choose even or odd. So you could, in principle, pick anything you want, but that's just going to make life hard for you. And even and odd is very nice. So let's see how many people got this one right. Great. So 75% of people figured out it depends. Hopefully, if you did figure out it depends, you see what it depends on. And indeed, the question is, what is it going to be, the even or the odd extension? So I have this tiny thing here. Won't let me zoom in. We always try to figure this out. Let's see if we can make it work. There we go. So depending on if you make an even extension, so an even extension is the one on the left here. You copy the function so that it's a reflection on the axis. And an odd extension, you flip it twice. So you flip it once across the x-axis, once across the y-axis. So if we look at what we're doing here for the function f of x equals x, we can either make it like this. This would be an even extension. Or we can make it just the function f of x equals x. So that would be an odd extension. So let me see how I would draw that on here. Let's draw another one in the corner here. This is the odd extension. So if somebody asks you to do this function f of x on 0, 2 and write it in terms of the world's most important orthogonal basis, the first thing you have to do is decide how you want to extend it to make it from -2 to 2. And you have sort of two obvious choices. And depending on which choice you pick, you'll either get all the sines are 0 or all the cosines are 0. We actually did this one already. So the even extension, this is what we did last time. So this was last time we did this function. And it turned out it was all the sines were 0, and we had this sequence in terms of cosines. So today we're going to do this function as a warm-up. We're going to do this right now. Okay, so that's what we're going to do to recap chapter 10.2. Okay, so let me get my notes here, make sure that we're doing this right. So we have the function f of x equals x on minus L to L, and L equals 2. We're doing it from -2 to 2. And the way I always do these, I start by writing the expansion that I want. So I got a0 times a half plus, and then I have the sum, m equals 1 to infinity. And I'm going to have am cosine of m pi x over L plus bm times the sine of m pi x over L. Okay. And because this function is an odd function, the cosine coefficients are all 0. So these are all 0. All 0 since f is even. Since f is odd. So cosine is an even function. If you write an odd function as a sum, all these will be 0. Okay, so this is f of x. And now to find the coefficients, we use the same trick we used last time, the orthogonal basis trick, which is we just take the inner product of both sides with the functions that we want. So a0 is equal to. In fact, I think it's also true, the function 1/2 is an even function. So I think why don't we also do this as well? Also 0. So all the a's are 0. We're left with the b's, so let's do this one. So I'm going to do the inner product of f. To extract the coefficient bm over here, I'm going to do the inner product with the sine function. Sine of n pi x over L. Okay, and here's something you can be careful of. Over here, m was going from 1 to infinity, and I was using m as this dummy variable in the sum. And over here, I'm extracting the nth coefficient. So it's good to keep track of what your variables mean. So I'm extracting the nth coefficient. So n is some arbitrary thing. M here was this thing ranging from 1 to infinity. N here is some fixed thing. Okay, so I do the inner product. And when you do the inner product, you get this inner product, the sum. So these were 0. I'm not going to write these again. But over here we have the sum from m equals 1 to infinity of bm sine of m pi x over L. And that inner product is going with sine of n pi x over L. And here's the point, is that these functions are orthogonal as long as m is not equal to n. So in this sum, after you pull this out, a lot of these terms are 0, and what are you left with is bn times the sine of n pi x over L times the sine of n pi x over L. Okay, and we know what this is. This is the integral of sine squared. This is worth writing down. This is the integral of sine squared. Let's write it like this, dot, dot, dot. Right, let's do dx. So it's something times dx n pi x over L, and it's from minus L to L. And so this is over some integer number of periods. So we're going to use the fact that this is, the average value is a half, and the length of the interval is 2L. So the total integral is the average value times the length of the interval, which is just L. So this is Bn times L. And on the other side, we have this inner product, and we can write that inner product as an integral. And that integral is, so it's the inner product of f with the sine, and f is the function f of x equals x. So this is the integral of x times the sine of n pi x over L dx from minus L to L. And that's equal to Bn times L. So that's the calculation we were doing last time. That's going to come up over and over again. If you remember all these steps, you can skip some of these steps. So like this first step, I think you could skip it if you can see directly that all the things are going to be 0. So going straight from here to here, I think is okay. Over here, from here to here, to remind you where the L comes from, is also okay. So all we got to do now is do this integral, which I'll do in a second. It's an integration by parts. And then we'll have the formula for Bn. And remember, L is 2 in our problem. I find it's helpful to leave the L as L until the last second to help me make sure I don't make mistakes. But if you want, you could have put that in earlier too. Okay. So I got to do the integral from minus L to L of x times the sine of n pi x over L dx. So I'm going to set up, when I do integration by parts, I make these little tables. You might do integration by parts a different way. You can do it however you want. So for me, when I do integration by parts, I have two functions. One function I'm doing the derivative of, the other function I'm doing the integral of. And to start with, I have to write something so that the product of the two things is what I want. And then I do pluses and minuses to keep track of the pluses and minuses in integration by parts. So out here I'm doing the derivative of this column. The derivative of x is 1. The derivative of 1 is 0. And I'm doing the integrals of this column. So the integral of sine of n pi x is cosine of n pi x over L. Then there's a times L over n pi. So that when you do the derivative, that comes out. And then there's also a minus sign, because the derivative of cosine is minus sign. Okay, good. And then you do the integral of that one more time. Get an L over n pi squared. Can we see the last part of the paper? Yeah, I can put that up while I'm doing this. Okay, and so reading off what's going on here. So to read off this integral table, you read the diagonals. So this is the function. Okay, it occurs to me there's something else we can do here that I was going to simplify things a little bit before I do the integration by parts, is instead of integrating from minus L to L, I'm going to integrate from 0 to L and multiply by 2. And we know that that'll work because these are both odd functions. So when you multiply two odd functions together, you get an even function. And an even function is the same from minus L to 0 as it is from 0 to L. So what I'm doing is, instead of integrating under the whole function, this is a bad picture. So it's supposed to be a copy. Instead of integrating everything from minus L to L, I'm going to integrate from 0 to L and multiply by 2. So I'm doing that area times 2 to get the full area. Okay, this example is also in the textbook. I think they do the same trick, but they don't tell you about it. Or maybe they tell you about it earlier or something. So that's a good trick whenever you're doing these integrals. Usually you can simplify the integral knowing that the function is even or odd. Okay. Yeah, if the function is odd, if you do the integral of an odd function from minus L to L, it's always 0. That's actually kind of what we used over here. So these a0s and am's, they have formulas that are integrals of odd functions. That's why they were 0. Or one way to see that they were 0. Okay, back to this integral. So I have minus x times L over n pi times the cosine of n pi x over L plus L over n pi squared times the sine of n pi x over L. Let me make sure this is the right thing. Yeah, and this is from 0 to L. Okay. So when you plug in, let's do this the long way. Let's plug in minus L times L over n pi times the cosine of n pi L over L. Plugging in L plus L over n pi squared times the sine. So I plugged in x equals L. This is plugging in x equals 0. When you plug in x equals 0, on this term there's an x, so that just gives you a 0. And over here you have a sine of 0, which is also 0. So sine of 0 minus 0. So this is the nice thing. When you plug in x equals 0, both of these terms are 0. So that's why it's easier to integrate from 0 to L. Okay, so we got 2 times all that. Okay, let's see what's going on here. So here it is very important to know the graphs of sine and cosine really well. So we have sine of n pi x. What does that look like? So the sine function looks like that, and the cosine function looks like that. So where is sine 0? It's 0 at 0, pi, 2 pi, 3 pi, and so on. So at integer multiples of pi, the sine function is 0. So this term right here, sine of n pi L over L, is precisely one of these points where sine hits 0. So this is equal to 0. That term goes away. So we're left with this cosine of n pi L over L. So now it's important to know the graph of cosine. And sine has zeros at these n pi's. Cosine is either plus or minus 1. So if we look at the graph of cosine down here, it's 0. It's plus 1 at x equals 0. So it goes plus 1. And then at x equals pi, it's minus 1. And at x equals 3 pi, at 2 pi rather, it's plus 1. And then here at 3 pi, it's minus 1. So at integer multiples of pi, it's either plus 1 or minus 1. At n pi, it's either plus 1 or minus 1. And it depends if n is even or odd. So cosine of n pi equals plus 1 if n is even. And cosine of n pi equals minus 1 if n odd. So you'll see this kind of thing come up. We know we had some even and odd type shenanigans last time as well, where all the odd terms were 0. Oh, I'm blocking the camera. That's funny. Okay. So in this problem, we have the cosine of n pi, and so it's going to be plus 1 or minus 1, depending on if it's odd or even. So I think the final answer is it's equal to, let's make sure we do it right. Is there a mistake somewhere? Maybe you guys can see. Is there a mistake? No, I think it's okay, actually. Okay, good. So we got minus 2L squared over n pi, and then it's plus 1 if n is even, and it's minus all this L squared over n pi times minus 1 if n odd. So I think that is the integral, minus 2L squared over n pi. And now the textbook does something funny that you should be aware of. And so this is perfectly valid. And the textbook writes this exact answer as the following. It writes it as minus 2L squared over n pi times minus 1 to the power n. They write it like that. And these two formulas are the same. So if n is even, you have minus 1 to an even power. That's just 1. And if n is odd, you have minus 1 to an odd power. So you get this thing. So these two things are exactly the same. Why is the textbook using this formula? The reason is it's shorter. So this is longer. You see I almost ran out of space here. So this is just saying it's either plus 1 or minus 1 depending on if n is even or odd. This one is saying the same thing, but it's hidden. So don't get confused by this notation when you see it in textbook. Like if you see this to the power n thing, it just means it's doing cases of if it's even or odd. So this answer is perfectly valid. I think this is more clear than this. That's the way the textbook does it. Okay, so that was the integral. That was twice the integral, and Bn is equal to 2 times the integral from 0 to L of x times the sine of n pi x over L dx over L. So remember, if we go back to our earlier thing, bn times L was this integral, so bn is the integral divided by L. So I would write it like this. It's equal to minus 2L over n pi if n even, and it's plus 2L over n pi if n odd. And the whole thing is that the function f of x is equal to the sum of bn times the sine of n pi x over L. N equals 1 to infinity. So we did the case n equal L equals 2, but we didn't actually use that anywhere, so this whole thing is totally valid for any other value of L as well. Okay, that's writing the function. So, you can write this more compactly. You can write this something like this. This is how the textbook does it. 2L over pi times the sum from n equals 1 to infinity minus 1 to the n, the minus sign, divided by n times the sine of n pi x over L. Okay. L squared, right? Not L. The reason the L squared became an L was because I divided by L. So to find bn, you have to take the integral and divide it by L. Yeah. Actually, you can always check units on these things as well. So bn's are supposed to have the same units as the f's. So n and pi are dimensionless and don't do anything, but L is like the dimension of what's going on here, because I have the function f of x equals x. So the inputs x ranges from minus L to L, so the output x also ranges from minus L to L. So actually, this is a good way to check, make sure you didn't make a mistake. Okay, that is basically what you're doing in chapter 2, or chapter 10.2. So we take functions, and we want to write the functions as sums of sines and cosines. And the reason we want to write them as sums and sines and cosines is because sines and cosines are going to be kind of like the eigenfunctions, and these coefficients are going to be like the coefficients C1, C2 from chapters 4 and 6. So that is the whole story from chapter 10.2, and we're going to use it a lot coming up, so it's kind of an introductory chapter. I think you guys have seen some Fourier stuff before, but it's good to remember how it works. I think you can get really confused by these Fourier things. I think the whole trick is this trick with the inner product. So you write your function as the sum of the things in the world's most important basis, and then you do inner products to find the coefficients. So if you want, you can memorize all sorts of formulas, but I think that this is the best way to do it. Sometimes things get a little more complicated, so it's good to do it this way. Okay, I'm going to open it up for questions on Top Hat right now, and we'll do a couple minutes of questions here, and then we're going to move on to something completely different. So let me close that up. Do questions. I think some people have figured out that the question problems were worth marks. They were not supposed to be. So now I made it so it says, no, these questions don't count for marks. So no need to answer with no. One person answered with nope, so I guess that's fine. We have 2 other people answering with no. Okay, and I'm going to sort by most liked. So if you see a question you like, you can upvote it. I'm going to upvote this one that says nope, because they didn't answer with no. Is the inner product, in the inner product, are they supposed to be n? Yeah, so, all right, let's go back to here. So you can use n and m however you want, but you just need to be careful and make sure you understand what it means. So in this sum, m means the variable of the sum. So it's like a dummy variable. It starts at 1. It goes 1, 2, 3, 4, all the way up to infinity, and it's this thing. Over here, I'm fixing some number n. So like I'm thinking of n equals 7 or n equals 3, like some fixed number n, and I'm calculating the nth coefficient by extracting the nth coefficient. Could I have said extract the mth coefficient here? Yes, that would be perfectly valid. So I could say m is 3 or m is 7. The thing is, if you do that, then now you have a confusion, because m now means 2 different things. So by using n here and m here, I avoid this like confusion of which is which. And so I think it's perfectly valid to say find the mth coefficient, but then you're going to have a confusion here because you're going to have an m in the sum, and you're going to have an m, the thing you're looking for, so then you get mixed up. So I think you should use 2 different letters for these 2 things. Which one is n and which one is m does not matter. You could also call them A and B or something, like whatever you want. I'm just using the same letters as the textbook. So M and N are the demi variables we use. Here it was some fixed thing. Here it was ranging from 1 to infinity. I don't want to use the same thing twice because then there's a confusion here. So by using two different things, I think this step was perfectly clear. Okay. Okay, good. Lots of questions here. Let's do these in order. Is there any good reason why we multiply a0 by a half? The good reason is because the textbook does it. So I would say you don't, like, no. There is some kind of reason that the like cosines and sines together are supposed to like match together to give something whose total norm is 2L. So there's some kind of like complex analysis reason that it makes sense to put a half here. But for what we're doing, there's no special reason except for the textbook does it. You could actually, I'd be fine if you do the whole problem with a 1. So we'll try to word the question so that a0 is always a thing in front of a half. But, you know, like, there's nothing special about a half. That's a great question. In the exam, will the Fourier series formula be given? No. I don't know what formula you want me to give. So did I use any formulas here? I think the one formula that I used was this thing, that the integral of sine squared is over an even number of periods is a half. We'll give you that formula. Maybe I'll list the orthonormal basis, the special basis. But actually it occurs to me that the exam's probably going to be some kind of open book exam, so I guess write down whatever formula you want. Okay. Can we leave the cosines and sines in the coefficients an and bn? I.e., do we need to simplify by breaking it up into what it's equal to when it's even or odd? Okay, yeah, so this is a good question here. So someone is saying, do I need to break this down into if it's even or odd? Well, so the fact is, it's +1 if it's even, and it's -1 if it's odd. So you have to write that information down somehow. One way is to write it down like this, and another way is to write it down like this. So you have to do one of those two things, or you just you don't have the correct formula for the bn. So can you leave the cosines and sines in the coefficients? So I guess is this breaking it down? Maybe not. You just have to write it down in some way that captures what the truth is, that the formula is one thing if it's even, it's something else if it's odd. I guess you could leave it as cosine of n pi, right? You could leave it like that. That's another way to write it. But I think that's it's better to write it like this, because like maybe the question is when is it positive, when is it negative, so you have to know that anyway. Why did we assume m equals n? Okay, that's a great question too. This also goes with the question below that, which is, can you re-explain why the coefficients are found using the inner product? So I think let's focus on what's going on here. This one is with an n. This is what I'm extracting the nth coefficient. This thing is a sum over all possible m values. So in this sum, we're going over 1, 2, 3. We're doing every single value. So m is a dummy variable that does every single value. N is some fixed value. But the fact is, this sine function, sine of m pi x over L, and sine of n pi x over L are orthogonal. That means that when I do this inner product, I get 0 unless n equals m. So actually, maybe the term I left off, this is, when you do this inner product, you get a bunch of zeros. You get infinitely many zeros, actually. So you get 0 plus 0 plus 0 plus dot, dot, dot. And then, miraculously, in the nth slot, when m equals n, you get something non-zero. And then afterwards, you get more and more zeros, plus 0, plus 0, plus 0, plus 0. So the reason n equals m, in quotes, I wouldn't say that n equals m. I would say that the only non-zero term is the term when m equals n. That's what I would say. All the other terms are 0, and which is why this whole orthogonal basis magic works. It sort of extracts the term you're looking for. Okay. So I'm not sure if that was clear or not. This is, again, review from last time. Okay. Someone said, where did you get the expression from the bottom of the first page? Is it this one? This one is rearranging this equation. So this equation and this equation are the same. Okay. I think that's all the questions. You can put another question in the chat or something quick if you want. But otherwise, we are going to move on to 10.3. So 10.3 seems completely different than chapter 10.2. It's on boundary value problems. And these two things really are completely different. The thing they have in common is they're both the building blocks of what we need in chapter 11. So we're going to need this Fourier stuff, which is kind of complicated. We spent more time on that. And we also need this like little thing from chapter 10.3, which is boundary value problems. So that's what we're going to do now. And I'm going to start the boundary value problems by letting you guys do some review from earlier, which is about the equation like y double prime plus 4y equals 0. So this was chapter 4. So you're working on this equation. You find the general solution. So we have the general solution. And you want to nail down a specific solution. So you want to go from general to one specific solution. Roughly speaking, how many, quote, pieces of information do you need to specify a solution? I'll just give a minute for this. So this is review. Hopefully, it shouldn't take too long. It's a good chance to ask another quick question if something I said confused you in the chat right now while I'm waiting for answers to come in. Okay, so for me there's 10 seconds left, so for you there's probably only 5 seconds left. Let's see what people said here. Responses, 73% of people said 2. 2 is the right answer. So when we're doing second order equations, like y double prime plus 4y equals 0, the solution in this case is c1 times the sine of 2t plus c2 times the cosine of 2t. And we have two numbers that we're looking for, c1 and c2. And sort of every piece of information gives you an equation involving c1 and c2. So you have two unknowns, so you're going to want two equations, so two pieces of information. And so very typically, so we need two pieces of info that gives two equations for C1, C2, and then you solve to find C1, C2. And so everything we've done in the course so far, we've always given you initial value problems. So we say y of 0 equals 2, and y prime of 0 equals 3, and that turns into the equations C1 times the sine of 0 plus C2 times the cosine of 0 equals 2. And then when you do the derivative, you get 2 times C1 times the cosine of 0 plus 2 times minus 2 times C2 times the sine of 0 equals 3. So when you do the derivative, the coefficients get multiplied by these 2's that come out of the sine and cosine. So the second equation, the first equation was C1 and C2. The second equation is 2C1 minus 2C2. So you have these equations for C1 and C2, and you solve them to get C1 and C2. So what are they in this case? I guess they're C2 equals 2 and C1 equals 3/2. So not so complicated. So the new thing in this chapter is instead of giving you information at one point, this is an initial value problem. Initial value problem. The only new thing in chapter 10.3 is instead of giving you the information at one point, I'm going to give you the information at 2 points. So I'm going to say y of 0, and the example I came up with, y of 0 equals 3, and y of pi by 4 equals 7. That's the example I gave you. This is called a boundary value problem. And that's what we're doing in chapter 10.3. This is a boundary. So the only difference is that instead of giving you the information at the same time at time 0, one is at time 0 and one is at time pi by 4. Two different time values. Okay, so if you solve this, you plug these in, you got C1 times the sine of 0 plus C2 times the cosine of 0 equals 3. Same kind of thing as before. Now we plug in this other thing at pi by 4. C1 times the sine 2 times pi by 4. So I'm plugging into this equation up here. Plus C2 times the cosine of 2 times pi by 4 equals 7. And I think if you solve these, the first equation, you can read off that C2 equals 3. And from the second equation, it turns out that you have a cosine of pi by 2. And cosine of pi by 2 is equal to 0. So the first equation actually says C1 equals, or the second equation rather says C1 equals 7. So this sine of pi by 2 is 1, and the cosine of pi by 2 is 0. So if you just do these things, you solve for C1 and C2. So, you know, same kind of game as before. Two equations. The types of equations you get are maybe slightly different, but everything else is okay. All right, question in the chat here. Won't the initial value be sufficient to find C1 and C2? Hence, just one info is needed. My thoughts. So one piece of information is needed if it is an equation of this form, a first order equation. So y prime equals 7y. So for a first order equation, then you only need one piece of information. For a second order equation, you need two pieces of information, C1 and C2. And the reason is because you have two unknown coefficients, C1 and C2, so you need two equations to solve them. Yeah, so just knowing y0 equals 2 is not enough to solve it. You need y0 equals 2 and the derivative. A good way to think about it is if you have a car and you want to know what the car does, you need to know where the car is and also how fast it's going. So it's position and velocity to figure out where it is. That's why we need two pieces of information for these second order equations. Okay, so that's what I had to say. That was my baby example. Now you guys are going to do one. Find the solution to y double prime plus 4y equals 0 with boundary conditions y of 0 equals 0, y of pi equals 0. So I gave you something that's just like the example I gave here, but I'm just having you guys do it. So I gave you two different pieces of information, one at time 0, one at time pi, and the question is, find the solution. Okay. So I'll give you a minute or two to work on that one. You gotta kind of just do what I did. I guess it helps to put this up here. Okay, time ran out, but now some people didn't answer. I'm going to reopen it for a little bit here. Okay, 18 seconds left. For you, there's probably less than 18 seconds left, so put in your guess. Most people have answered. I got a few people at the end here. Okay, so let's remember what we're doing. The whole point is we have the general solution. That's a family of functions. The general solution is lots and lots of different possible functions. And then we take two pieces of information and we hopefully narrow it down to one specific function. So let's see what you guys said, if you found that one function. Okay, so lots of people found the function 0. So 0 is c1 equals 0, c2 equals 0. The second one, the second most common answer, people wrote 0, 0, so I guess they found c1 and c2 are 0. So that's the function. People are found the function. Found the function y of t equals 0. This is 0 times sine of 2t plus 0 times cosine of 2t. Let's see what other people wrote. So some people, I think, figured out the right thing looking at the answers here. Let me put that up. So some people have some things about this answer is interesting. c1 times the sine of 2t. There's a few like that. And I want to tell you this is one of those patented trick questions. So this y of t equals 0. This is not the right answer. Not the right answer. So there's something missing here that I think that tricked most of you. So I'm going to open it up again. Maybe you can write in the chat, what was the trick? So in chat, what's the trick? Maybe trick's the wrong word, but the answer is not this function. The answer is not 0, 0. So that's the thing. I want you to explain why it doesn't have to be. Okay, so I'll give you a little bit of time on that. Maybe I'll reopen this. You can try to put in a better answer if you want in Top Hat. And while you guys are answering this, I'm going to set up this system. So you should have got a system of equations by plugging in. And I'm going to find what that system is. So we did y of 0 equals 0, y of pi equals 0. Okay, I think people in the chat have figured out what's going on here. We were given two pieces of information. That led to two equations. So following along with what happened here, we got two pieces of information, two equations. But then when you look at the two equations, it's actually the same equation twice. So there were two pieces of information and two equations, but the two equations were kind of repeats of each other. They didn't have enough information to find C1 and C2. So in what we did earlier, in initial value problems and in the example I gave before, we had two sort of non-degenerate equations. So from linear algebra, if you have two equations, sometimes there's one solution, sometimes there's many. If they're sort of normal, then there are two solutions. So this was the typical thing to happen. This is the atypical thing to happen. So what is the trick? I would say we got a degenerate equations. So these equations don't specify what C1 is. So C2 is 0, but C1 can be anything. And what that means is y of t is 0. It's not the right answer because it is not the only solution. Not the only. So there are other solutions, and the other solutions are any multiple yt equals c1 times the sine of 2t. That is always for no matter what sign c1 is. No matter what c1 is. So this is the only trick about boundary value problems. Why are boundary value problems more difficult than initial value problems? Initial value problems are guaranteed to never be non-degenerate. I guess they're never degenerate. Initial value problems always come out. You can always solve the equations. You always get C1 and C2. For boundary value problems, something can go wrong, and you end up with this situation where there are infinitely many solutions. There's more than one answer. Any multiple of sine will work. So there's not one answer to the boundary value problem. So initial value problems always have one answer if you have two pieces of information. But boundary value problems, something can go wrong. You can have lots and lots. And the thing you want to recognize is, when does this happen? When does that happen? And it has something to do with the equation. So here is the last question of the day. For which values of lambda will the equation y double prime plus lambda y equals 0, y of 0 equals 0, y of pi equals 0 have non-zero solutions? So when does this issue happen? For what values of lambda? Let me see if I can make this bigger. Nope, can't make it bigger. Oh, okay, look, there we go. Okay, let me add a 60-second timer here. So here is how I approach this problem. If you're finishing up, you can finish up in Top Hat. I'm going to tell you what I did. So I found the general solution, which involved the square root of lambda and sines and cosines. Then I took my two pieces of information and turned them into two equations by plugging them in. The first equation just says C2 equals 0. The second equation is this funny thing involving sine and cosine. But if you plug in C2 equals 0, what you end up with is that C1 times the sine of square root lambda pi equals 0. So if the sine of square root lambda pi is not 0, then C1 has to be 0. But if the sine of square root lambda pi is equal to 0, then this is degenerate. It doesn't have any information. So that's what happened in the example I gave you before. So when lambda was 4, when lambda equals 4, sine of square root lambda pi equals 0. That's what happened in the example I gave you, and it was degenerate. So the thing that needs to happen is this is degenerate when square root lambda times pi equals 0. And now again, you have to know the graph of sine. So the graph of sine, what does it look like? Here's sine, it goes like that, sine of x. It has zeros at 0, pi, 2 pi, 3 pi. So degenerate when the sine of square root lambda pi equals 0. When is the sine of something 0? The sine is 0 when the input is something times pi. So the sine of this number is equal to 0 if square root lambda pi equals n pi for some value of n, for some integer n. And finally, if you just cancel out the pi's, this says lambda equals n squared. Lambda equals n squared. So before we had lambda equals 4, that was 2 squared. The other values that work are 1 squared, 1, or 9, and so on. So you could write the answer as a list. So lambda equals 1 or 4 or 9 or 16 or 25 or ... There's infinitely many values of lambda that work. This is how I got to the n squared. Somebody wrote in the chat, the period is a multiple of the distance. That is very close to being correct, or it's on the right track. Be careful here, though, that pi is sort of the half period of sine. So it has to do with the zeros of sine, not the period of sine. So you'd be off by a factor of 2 if you mix that up. The other thing you might mess up is the square. So it's easy to forget about the square. The square came from doing the solution to this thing, even though it has a lambda. The solution has a square root of lambda. So that's the final answer. Lambda equals n squared. I wonder what people said. Even, odd, positive. Square root to be non-even. So one person wrote perfect squares. That's great. So perfect squares will work. What if lambda is negative? If lambda is negative, then you don't have this problem. So for what values of lambda do you have this thing? Only positive values of lambda work. Which positive values? Only squares. So negative values won't work. I think very few people got it. Okay, so good. I'm glad you guys. There's something new to be seen there. Okay, so this problem, this thing is sometimes called an eigenfunction problem. Eigenfunction problem. So these are the boundary values. And the reason it's called an eigenfunction problem we'll see on Thursday's class. So we're going to take everything we did last class and today. So all this stuff about Fourier series, all this stuff about boundary values, and this eigenfunction problem, this lambda equals n squared shenanigan, and we're going to combine that all to solve PDEs. Does a perfect square make it degenerate or non-degenerate? It makes it degenerate. It means that there are non-trivial solutions to this. So that's degenerate. You would think that the only solution is the zero solution, but it's degenerate because there's infinitely many solutions. That was the question. So for which values of lambda does it have non-zero solutions? Lambda equals n squared is when it has non-zero solutions. Okay. The last thing is questions. So I'll leave this open for questions in the chat. I'll stick around for a bit, but those are all the things. On Thursday, we're going to start PDEs, which is like a whole new world of stuff. There are 2 YouTube videos about PDEs that are very nice, have lots of pictures, and will give you a nice gentle introduction to what we're going to be doing before we get hardcore into the math. So definitely watch those. Those are like pre-class watching homework. There's like a little quiz with like, did you watch it? That should be super easy, and there's no web work this week to make up for having to do that. Someone said, are there any updates on the exam? Yeah, we're working on it, and that will come soon. It's probably going to be like an online thing on Quarkus. We're trying to figure out exactly what it's going to be and like how to reweight everything. So we'll have something out by sort of the end of the day on that. Lots of people said no. One person said nop. That's good. Okay, so yeah, that's it for me. Oh yeah, so somebody in the chat wrote, if lambda is negative, then the solution doesn't have sines and cosines. So that is true. So probably what I said earlier was not sufficient justification. So I think it is true that it's always non-degenerate. The only solution is the zero solution when lambda is negative, but you should check with exponentials. So when I did this, I assumed lambda was positive. And I shouldn't have done that. So this is only works if lambda positive. So lambda negative, you should check, but it will be true that the only solution is a zero solution. Yeah, that's a good point. Maybe I'll do that. That'll come up at some point, probably. Okay. Are we reweighting it? Yeah, it's going to be reweighted. If it's degenerate, there are infinitely many solutions. So you would like it to be like this problem where there's only one. So 2 pieces of information gives you 1 solution. That's the sort of non-degenerate case, the regular case. You give me the 2 pieces of information, I give you the solution. The degenerate case is when it happens, that there are infinitely many solutions. So in this example, when it's degenerate, then any value of C1 works. So there's infinitely many solutions. So that's why it's degenerate. I gave you 2 pieces of information. You were supposed to have only one answer, but there's infinitely many answers. That's why it's degenerate. So there's infinitely many solutions. All of the solutions are non-zero solutions. Well, okay, there's also the zero solution, but the problem is that in addition to the zero solution, there's infinitely many other solutions. Okay. So we're gonna send an update about the exam at the end of the day it'll be on Corgus. So I don't have the answers to your exam questions right now. When are quiz marks coming out? That'll also be sometime this week soon. Okay, I think that's all the answers to the questions that you guys have. So I'm going to stop here. Okay, take care, guys. Talk soon.